I mean, not yet. Maybe I'll do such a terrible job that you won't thank me. Good point. All right, so that's a first of 3 lectures, and I want to start by talking a little bit about quantum groups. And their forms. And then I will talk about the quantum category O itself. So let's start by introducing some fairly standard notation. G, small g, is going to denote a simple V algebra. And to save myself, and also you guys, some headache, I want to assume that it's simply laced. And it's just to simplify the exposition. So simply laced means types AD. So inside of G, I'm going to consider a Cartan subalgebra, which I'm going to call A. And then inside of H dual, I want to consider weight and root lattices that I'm going to denote by lambda and lambda 0. So these are weight and root lattices. Then I want to consider the set of simple roots. Alpha I, where I is in some indexing set, I. Yes. It's simple roots. And then I can have the Cartan matrix. Aj. And finally, I want to have the invariant form on H dual. There are C many choices, and I want a standard normalization with alpha I paired with alpha j. It's going to be Aj. So these are the notations, and finally, to start talking about quantum groups, I will need to fix an indeterminate, which I will call V. And then I can consider the field of rational functions in this indeterminate. You see V in round brackets. Okay. Well, let me recall the generic version of the quantum group due to Dringfeld and Jimbo. And this is going to be denoted by U sub V of G. This is an algebra over this field of rational functions. So an associative algebra with the following generators. So as usual, I want generators called EI and FI, where I is in the indexing set for the simple roots. And then I want generators that I will call K nu, where nu now is in the weight lattice. Okay. Sometimes this is called simply connected form. And then I have a bunch of relations I want to write down, just in case you haven't seen them. So first, there are relations on case, which say that K0 is a unit, and then K multiply like elements in the group algebra of lambda. Okay. Then we have commutation relations between case and is. And this commutator is v to power nu paired with alpha I, ei, and then similarly with f's. But now v is with in the opposite power. A more interesting relation is a relation for the commutator of E and F. Ei is Fj. And this is equal to delta Ij is a Kronecker symbol times K alpha I minus K alpha I minus 1 over V minus V2 minus 1. Okay. And finally, there are so-called quantum cell relations. Which in our simply laced case just says the following. They say that, well, let me write relations for E's. So Ei and Ej commute if Aij is equal to 0. And then there is a following funny relation. Ei squared Ej plus Ej Ei squared is equal to V plus V inverse Ei Ej Ei. And this is in the case when Aij is equal to minus 1. And then there are completely analogous relations for F. Questions? So this is a quantum group over this field, the generic one. And that's not what I want to consider, actually. What I want to consider are certain forms and specializations of this generic quantum group. So what do I mean by forms? So forms are subalgebras over the algebra of Laurent polynomials. Let me give them temporary name A. So this lives inside of U of G. Such that when I base change back to the rational functions, so this guy now is a subalgebra of U with G living over its field of definition. I want this to coincide with the entire U with G. Okay. So that's what I mean by form, and then later on I will explain what I mean by specializations. And to find the forms that we need, I will require a little bit more of notation. When I take some non-negative integer n, I will have a so-called quantum integer. Which I will denote by n in square brackets. And who is that? This is v to power n minus 1 plus v to power n minus 3 plus blah, 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 plus v to power 1 minus n, or you can write it as v to power n minus v to power minus n, or v minus v to minus 1. As the name comes because when you set v equal 1, you recover the original integer n. Now, for the same price, I can introduce the quantum factorial, denoted with a trig sign. So as usual, it's a product of the first n quantum integers. And then I can consider the so-called divided power element. Let's say we'll take ki divided power n. So now n is in round brackets. Now that's by definition ei to power n divided by n quantum factorial. And this is a legitimate element in my algebra u v of g. And then completely similarly, I have fi divided power, living in the same algebra. Okay. So that's the notation I want. And I'm going to define not one, but whole three forms of this Greenfield-Jimba quantum group. So the first one is kind of the most naive one. And it has a name, it's called the Concini-Katz form. UV with superscript dk. And so who is that? That's just a subalgebra of Laurent polynomials with the same generators as for the initial quantum. Generated by ei power n, fi to power n, and k news, where I runs over I, n runs over non-negative integer. Well, I can take positive integers, I guess. And nu runs over. Kind of to define this form, you don't really need to apply any imagination. Turns out that to study representations, you need to apply a lot of imagination. Okay. And that sort of this definition gives a general pattern of how this how these things are defined. You take the generators and then you kind of mess up with the powers. In a way that you will be dividing them by, well, exactly this element.
You don't need n here.
Good point, but let me keep it uniform. Sasha was teaching algebra at some point recently. Then next there is a so-called Lustig form. And it's so it has its own notation ULV. And it's generated by the elements EI to divided power n, Fi to divided power n, and K nu, well, where these letters are rung over the same kind of sets. And finally, and most importantly for this lecture series, there is a so-called mixed form. And for the mixed form, I will include the divided powers in EIs, but not in FIs. Yeah.
In the first form that you discussed, how do you define the commutator between EI and FJ?
I don't need to define it. It's just the same element as before. That's a subalgebra generated by this element. You can then ask how to present it by generators and relations.
Okay.
And the presentation is essentially the same, unless your V is plus minus 1, where you need to say a little something.
So even though we can't invert V or V inverse very formally, we still have elements of this form in there. Okay.
What you have for V plus minus 1 is not going to behave particularly well, maybe, but you know, it's in principle makes sense. Just a little optional comment. So some people in the room know about Drinfeld doubles, and that's essentially the Drinfeld double, the mixed form. More questions? Now, of course, you can ask, why would I care about these forms? And the point is that with forms, I can just specialize V to some complex number, something that I cannot do with a quantum group defined over rational functions. And that's what specializations refer to. So for some non-zero complex number Q, I can consider specializations of one of this algebra. Let me again call it A. And so what it is, for example, I can consider U mix. So what is this? It's UV mix tensor over Laurent polynomials. This is sub Q, and C sub Q is just the usual algebra C. U here just indicates that the homomorphism from here to here sends V to Q. And that's an algebra over C. Now, with the specializations, there are essentially two cases. One is easy and one is difficult. An easy case is that when your Q is not a root of unity, then all these quantum integers are non-zero. Okay? So just look at this number. If I specialize V away from root of unity, this number is never zero. So this n quantum factorial specialized at Q, let me denote it like this, is not zero. And therefore, there is no difference between the three forms specialized to ZQ. So UQdk is the same as UQ mix, and the same as UQ Lustig. That's because it's, you can further localize your ring of Laurent polynomials away from that Q. And in its localization, this is the same variable. Now, if Q is a root of unity, let's say that it's D's primitive root of unity. Then we are guaranteed that quantum D valued at Q is 0. And when your D is even, you even know that D over 2 sub Q is equal to 0. So in this case, the specializations are genuinely different and their representations behave differently. So UQ decay, UQ Lustig and UQ mix are different. Questions?
What happened to the generators when they are multiples of T? On those specializations, what happens to the generator?
For example, if you look at the Lustig form and you look at this element, they become 0.
Yeah. So you define them to become 0, or
Especially force them to become 0 by considering these elements in my form.
yeah, this one.
You can further ask what generates the specializations. The answer is known. For example, for Lustig form, you need EIs, FIs, K news, and also D's divided powers. Still a finitely generated algebra. Now, one of course can ask, why should I care about specializations, especially specializations to root of unity? And there are various answers you can give. In particular, there are several motivations using representation theory. There are also motivations from quantum topology, which I'm going to omit. The first one, I think historically, is a connection to modular representations. Modular means mod P representations. The objects I want to represent the Lie algebra. So this will be the algebra, say, over FP bar. Or maybe I want to start representations of the corresponding simple algebraic group of FP bar. I don't want to comment too much about this. So the story for the algebraic group is parallel to the story about the Lustig form. Stated precisely means that the representation theory of the Lustig form behaves structurally very much in the representation theory of the corresponding classical algebraic group. But in some sense, it's simpler and in fact can be used to understand the representations of the algebraic group. So this story is parallel to UQ Lustig. Let me maybe write epsilon for root of unity. epsilon here is dth root of unity. And this is best understood case. For example, the character formulas for this were discovered like roughly 30 years ago and quickly used to understand the character formulas for this group when P is very large. They turn out to be the same. Now, the representational theory of the Lie algebra corresponds to representations of U epsilon dk. But somehow that's kind of the easiest guy. Fine. In fact, there are very many basic questions we don't understand about representations of the Konchini-Katz form. So this is kind of hardest to understand.
Which D do you use?
So if you want to literally have this connection, D is equal to P. In the lectures, D is going to be some odd number. And so for this lecture, I care about, for this lecture series, we'll care about the mixed form.
Are there character formulas for the Konchini-Katz?
That's complicated. So for a suitable category, for suitable representations here, there are character formulas in some sense. Here, not yet.
But it's not like a variant of a wild character. It's something very different.
It's a bit subtle. I can just send you to read my paper with Rukovnikov from 2020, although that's kind of cruel.
Okay.
It's complicated. All right. So that's what I care about. I think in the third lecture, maybe, or well, the third lecture, I will try to explain why I care about this. For now, let me just pass to the second part of today's lecture, talking about quantum category. To begin, let me point out that actually all of my forms are graded algebras, in particular UV mix. So UV mix and therefore U epsilon mix, where epsilon is still dth root of unity, are graded by lambda 0 in the following fashion. So degree of Fi is minus alpha I. Degree of K nu is 0. Degree of EI divided power n is n times alpha I. Okay. And once I have a graded algebra, I can consider its graded modules. So U epsilon mix mod. What are those? These are modules over U epsilon mix together with a grading by lambda 0. Subject to natural operations, for example, when I apply a homogeneous element in this algebra to a homogeneous element in this module, the degrees add together. And then in this category, I have homomorphisms, which are module maps preserving the grading.
It is radical by lambda or lambda naught?
Lambda 0. So it's lambda. You can do lambda, but lambda 0 is just a bit easier. And for the same price. Okay. So now that's the main definition for this course. I can define for you quantum category O. The notation that I'm going to use is all epsilon mix. And so who is this? It's going to be a full subcategory in the category of U epsilon mix graded modules, consisting of modules with the following three properties. So whenever I write it this way, it means that that's a full subcategory. So what are the conditions? So first, I want my M to be finitely generated over U epsilon mix. That's relatively innocent. Second of all, I want a specified action of the elements K nu on a graded piece. So K nu, restricted to M sub mu, is going to act by scalar, and the scalar is epsilon to power nu pairing with mu. And finally, well, it's category O, so there should be some condition like saying that weights are bounded from above. And here it is. So the set of mu, like that M of mu is different from 0, is bounded from above. Let me just write down what this means formally. It means that there is mu depending on M, such that if M sub mu is non-zero, then mu sub M minus mu is a sum of simple roots with some negative coefficients.
So these MUs are supposed to be weight spaces, and
Yeah,
but you only have these for not all weights, but just roots.
yeah.
I see. Okay.
So there is a block decomposition for my category O, and perhaps when my D is not too small, every block in that larger category will be equivalent to a block in the smaller category. That's why I only want root letters. More questions? Let me finish this part with an example of an object, and it's kind of it's not a very expensive example. That's example of a Verma module. If I start with lambda in lambda 0, we produce the following module, which I will denote delta sub epsilon of lambda. And it's going to be the quotient of U epsilon mix. Y is the left ideal generated by the following elements. So I want elements k nu minus epsilon power lambda paired with nu. The same thing which appears in condition 2. And I want elements ei divided power n. And here, so nu runs over lambda, I runs over I, and it's any positive. Okay. What's the point? If we look at the class of 1, it's going to be highest vector of weight lambda. Okay. And that's not the end of this definition. Why? Because I need to impose a grading. Modules are graded by definition. And I want that highest weight vector, the class of 1, to be in degree lambda. Okay. And then I have induced grading on this entire model. Tom?
Is this the same as to say that these things are all graded, these things you quotiented by, is that the induced grading? Or are they?
Yeah.
Okay.
Well, for literally speaking, induced grading, I will need to put 1 in degree 0. And I put it in degree lambda.
Oh, okay.
So that it's now consistent with this. Okay. If I put 1 in degree 0, then here I will need to have lambda equal to 0.
Okay, yeah.
So I will just have k nu minus 1. Okay. So this is a legitimate object in my category. That's let me leave it as a little exercise. All right. Now let me make some remarks. Well, 2.1 is missing somewhere. So remark number 1 is that nowhere in this definition I use that epsilon is a root of unity. So if epsilon is not a root of unity, then, well, all my specializations are the same. So I will just write for epsilon. Still makes sense, as I said. But now the grading that I had to impose becomes a condition. You can read it exactly from condition number 2. Condition is just saying that k nu's act by powers of epsilon. Okay. And grading is recovered from actions of k. For root of unity, I had to impose grading as an additional condition because when epsilon is a root of unity, many of these numbers will be the same. But when epsilon is not a root of unity, you read this power from this, you read this exponent from the power. And you can ask, what is this category? Well, the answer is no. In fact, epsilon is equivalent to our good old friend, BGG category. However, when epsilon is the root of unity, the category is much more complicated, and kind of the goal of this talk is to explain what structure it has. The second remark has to do with my comment that kind of the initial motivation to study representations of the specializations of quantum groups has to do with modular representation theory. So you could ask, what is the classical modular analog of this category O? And the answer is not so difficult. Let me introduce some notation. So let me write F for FP bar. Then I can have the corresponding Lie algebra, GF. And I'm going to consider the Borel subgroup, B sub F inside of the corresponding algebraic group. And so what I can do now, I can consider the category which I'm going to call GF, BF naught. Let me tell you who those guys are. These are M, which are representations of the universal enveloping algebra, and also rational representations of the group. Such that we have the following compatibility conditions. So first of all, we want the structure map of a module to be equivariant with respect to the Borel. That's one condition. And another condition gives you the coincidence of two actions of the Lie algebra of B. Namely, that we want that the differential of the action of the group which is an action of the Lie algebra of B on the module, is the same as the action of BF sitting inside of GF. So these are the two conditions. This condition has a name. It's usually called strongly BF equivalence. This is weak equivalence. This is strong equivalence. And so how does this work? How does the parallel work? So BF decomposes as a product, semi-direct product of the torus and the maximal unipotent group. Okay? The action of the torus gives you a grading. That's a weight decomposition from above. And then what corresponds to the action of the maximal unipotent group? It's the fact that in my mixed form I have divided powers of the genus EI. And kind of the action of the maximal unipotent subgroup can be exchanged to action of classical divided powers. All right, are there questions?
I have a question. So you made the remark that U mixed was Greenfield double. How about this classical?
The same.
Double of what?
Well, I mean, you have two dual Hopf algebras, which is kind of the algebra with divided powers.
So one is
This
linear,
was the original algebra,
one is linear enveloping.
and the other is hyperalgebra. Meaning the algebra with divided powers. I do recall we are writing a paper about this stuff, right?
I'm recalling now.
All right. So last thing for today, I want to start a discussion of block decompositions that I've already mentioned. Remaining 5 minutes. And so it turns out that like many other instances of category O, this category O epsilon mix decomposes into the direct sum of subcategories. I'm going to call blocks, although strictly speaking, they should be called infinitesimal. Let me tell you what indexes this decomposition. And for this, I will need to introduce a very important player in this lecture series called the affine while group. I'm going to denote by W super A, and it's a semi-direct product of W, the usual while group, with the root lattice. And this group is going to act on lambda 0 itself in the following fashion. So first of all, let me take an element in the finite part, in W. Then I consider the usual row shifted action. So W applied to lambda is W lambda plus rho minus rho, where rho is just half the sum of positive roots. Then inside of my affine while group, I have the lattice part. Let me tell you how the lattice elements act. So if I have mu inside of lambda, then let me write T sub mu for the same element, 0, sitting inside of the affine while group. And I need to tell you what is T sub mu applied to lambda. That's by definition lambda plus d times mu. Let me write d so that it's distinguishable from alpha. And so who is d? It's the order of the root of unity, which was some odd integer. So for me, epsilon is this root of unity primitive. And d is odd. So I have this action, and it has some number of orbits. In fact, finitely many orbits. So now let me finish this talk with the definition, and then quick result. So definition for a WA orbit that I'm going to denote by theta inside of lambda 0, let epsilon theta is a full subcategory in O epsilon mix consisting of such modules M with the following condition. So M admits a filtration. And by this I mean a finite filtration by quotients of delta epsilon lambda of the subarma modules, like here, with lambda in theta.
Just to parallel with the usual BGG category O, is it BGG category O with like some kind of integer central character? Like is the when you say O epsilon is the BGG category O,
Yeah.
can a block be like a block of irrational?
No.
Oh, okay, okay.
But that's all blocks are integral.
Okay, great.
In
That's-
both setups, you can talk about non-integral blocks. In fact, in quantum setup, it's considerably more interesting than in the classical one. But I only consider integral blocks.
Okay, great, thanks.
And so why would I introduce this peculiarly looking category? The reason is the following proposition. Is that in fact O epsilon mix the component is a direct sum of the subcategories. O epsilon theta, where theta runs over all possible W super A orbits. And so the goal, in fact, for this lecture series is to understand the structure of each individual block. All right. Are there questions?
Question, sorry. So just type, so M admits filtration, meaning that like the quotients of this filtration
Yeah.
are quotients of
Yep.
delta epsilon. Okay, cool.
That's right.
Is this a highest weight category?
Yes. In a suitable sense. I'll talk about this maybe in the end of the next lecture, maybe in lecture number 3.
Does it have enough projectors?
No, it's, it's a very humble category. It doesn't have much of anything. It has Verma modules. It has the irreducible quotients. That's about it.
Great.
Well, I wouldn't say it's great, Usually in the world, the more you have, the better. Maybe so sorry, to separate you from the coffee. One final remark. So of course, like in the usual category O, here the simples are parameterized by highest weights, but the simples themselves are not particularly interesting. They're all finite dimension. That's the same story that you are going to have here. What is interesting is kind of the overall structure. And notice that Verma modules are infinite dimensions, therefore they have infinite lengths. All right.
Are there any more questions for the speaker? Okay, now let us thank the speaker. There will be coffee outside and we will have 10 minutes. Okay, 7 minutes.
Yeah, very good things. I haven't had a chance to put it on the. Thought they are.
Yeah, I think it's great.
Next talk is at 3:20, instead of.
Genio is just so 2 instances of the root lattice here. So we want to denote by this elements u here.
Like recognize you. Yeah.